Hello, everybody, and welcome back to the I Heart Pluto Speakers Series. We have a theme for our series of Worlds Revealed. And so every night we'll be having a speaker talking about their interpretation of revealing new worlds to us. This is now through the 21st of February. Tonight is the third talk in this series. And we have Dr. Richard Binzel tonight, and he will be speaking about undaunted exploration. But before we get to his talk, let me just tell you a little bit about his background. Rick and I were colleagues for more than a decade at MIT, and so it's my pleasure really to welcome him here tonight. He's recently retired from a 30-year teaching career at MIT as a professor of planetary science and joint professor of aerospace engineering. His astronomical observing expertise spans from asteroids near the Earth to distant Pluto and the Kuiper Belt, specializing in reconnaissance measurements that help define the science objectives for solar system exploration missions. He's a recipient of NASA's Silver Achievement Medal, the second highest honor bestowed by NASA to a civilian scientist. So we're going to be starting the talk very shortly. My name is Amanda Bosch. I'm a planetary scientist here at Lowell Observatory and also the Chief Operating Officer. I'm going to be looking for questions, so if you would like to put questions into the chat, we'll be answering them. We're going to probably try to leave them toward the end of the talk, but if you have some questions about a certain slide, feel free to go ahead and ask them as we go along. I would also like to mention that tonight's video sponsor is Findlay Toyota of Flagstaff. So with that, I'm going to turn it over to Dr. Rick Binzel and to tell us all about undaunted exploration. Thank you, Rick.
Well, thank you, Amanda, and thank you for the introduction. And here in the Zoom universe, I'm going to start sharing my slides and my screen, and hopefully you'll have that first slide up with the title there, Undaunted Exploration. So this is going to be a story of exploration, and it's going to be a mix of science, but also a lot about people, about who are the people who do these missions, who are exploring our universe or our solar system. And so because it's one person giving the talk, it's going to have a little bit of an autobiography flavor to it, but that's unintentional, or at least I have to ask for your forgiveness for just the quick intro here. And so I'll just start by saying, we all come from someplace, and so you can ask the question: how does a kid with a telescope who grows up in a farming community in Ohio get to the launch pad in their career? And I think for a lot of us who are in science, or no matter what it is we've been able to do, it starts with our passion, whatever it is that we find is our curiosity is passionate about, support from parents who help nurture that passion or support that passion and that curiosity. And in my case, grandparents. My grandfather was an MIT chemical engineer, and he stimulated a lot of my scientific creativity. But also, just in my own case along the way, a lot of my education and early career research came from fellowships and support. And it could have been from national agencies like NASA, National Science Foundation, but also from universities. And a lot of those came through benefactors, as programs like the Friends of Lowell Observatory and things like that. So this isn't intended to be a commercial, but other than to say that if you're a benefactor to your university or to Lowell, and this is supporting young students or early career scientists, I can just tell you, in my case, it mattered an enormous amount. And it's just good to let you know that what you do has impact. So I'm going to take this to a higher level to start and just ask the question, why do we explore? So this is undaunted exploration, but why do we explore in the first place? And there's a couple of ways to answer this. We're human, we're curious. Our species has always been curious, and that's still the same today. And we're just born curious, as anyone who interacts with small children or even big children knows. We are just born curious. But even more to that, I think exploration is simply a basic human instinct that is rooted to our survival. That if we weren't curious and if we weren't driven to explore, our species would not have survived. We would not have migrated and to new places, and it was a key to our human survival. So I think it's deeply rooted in us. That exploration is deeply rooted in us, and it's deeply rooted in what we do today. And this is a NASA chart about NASA explorers, and it's deeply rooted to all the different ways that your tax dollars basically go to explore the universe, and whether it's galaxies and things in distant deep space, the sun or the planets, there's an enormous program of space exploration that our nation funds and major nations do, from Europe to Japan, China, Russia, just a major we're all driven to explore. So with that, I'm not going to talk about all those missions in the NASA suite that was on the previous slide, but I'm going to talk about 4 missions. So these are 4 missions that I am a part of as a mission scientist, and talk about these in a little bit random order, but they range from asteroids near the Earth to asteroids in the main belt to asteroids out at the distance of Jupiter, and then the one that this audience is most familiar with, the New Horizons spacecraft that went all the way out to Pluto. And so I'm going to talk about these in a little bit of a random order, or seemingly random order. And the first of these is the mission called Psyche. The mission called Psyche goes to an asteroid named Psyche. And what's special about Psyche is we think that this asteroid in the main belt between Mars and Jupiter is sort of a crime scene, that there was a major collision of a large asteroid. We know that a lot of the asteroids are collisional fragments, but we think that there was at least one large object trying to grow itself into a planet. So we would have called it a protoplanet. It was trying to grow itself into a planet, but there was a hit and run collision that broke it apart, and that all that was left behind was an iron core. And so this is now what we see in the asteroid belt, looks like a 200-kilometer iron core. And when you think about the Earth, and we know the Earth has an iron core, but we can never explore the core of the Earth. We can never reach it. We just simply can't drill down into it. But we have meteorites. I'm not sure how well this shows up, but we have meteorites as samples of iron meteorites, of iron cores of bodies in the asteroid belt. But we've never seen one up close in its native environment. And so the Psyche mission is a way of going and looking, perhaps if we're correct about this object being an iron core, we'll be able to explore what does the inside of a planet look like. And anyway, that's pretty exciting. So Psyche is the mission. Psyche 2 Psyche is scheduled for launch in August of this year. It's a Falcon 9 Heavy, so that launch should be pretty exciting. Space exploration is a patient game. It takes 4 years after launch to arrive at our destination. And then the way I got involved in this is I studied Psyche, the asteroid, more than 25 years ago, when I was using instruments called a spectrograph to look at the colors and try to discern the composition of the asteroid. But we knew its reflectance colors indicated maybe it was metallic. And I wanted to see whether any of this mantle material, this other material around the core, was still stuck on the side of this object. And basically, these measurements are basically looking at different rotations of the asteroids. There's no change in the squiggles or the data points. And it just said that this may, in fact, be, if you pardon my expression, may be a naked metal core there in the asteroid belt. So it's very exciting, a chance to go and see something that we've never seen before in the asteroid belt. So that's all I'm going to say about the first of the 4 missions, Psyche. The next one is a mission called OsirisRex. This is an asteroid sample return mission. And we launched OsirisRex in 2016. We arrived at our destination, an asteroid named Bennu, in 2018. Bennu is an asteroid that's not so far in its orbit from the Earth, and it returns to the Earth in 2023. And I'll give you the story of Osiris Rex here. Osiris Rex is very special to MIT. In fact, MIT shows up on the logo for the mission. And in fact, that logo is there painted on the side of this Atlas V rocket. And so I like to say that this Atlas V was the largest MIT rocket ever launched. You see how you always claim things for your own university. And but what made this special, what made the OsirisRex mission and this launch special from an MIT point of view, was a small shoebox size instrument mounted on the side. You can see it with the arrow there. And the instrument is called Rexus. And what's special about Rexus is that it was designed, built, flown, and operated by MIT students. So if you're past your college years, imagine what it would have been like to be able to build and fly a space experiment as a student. And really, we tried to give them a fantastic experience. So Rexus, of course, is an acronym for Regolith X-ray Imaging Spectrometer. And those words probably don't help very much. This slide just shows you some of the students and grown-ups involved in the mission, but also many different parts of our university collaborating with NASA. And this was even a case of MIT working together with Harvard, with many excellent colleagues at Harvard, and very fortunate to work with such fine people. Okay, so Rexus and X-ray imaging spectrometer doesn't help very much, but here's maybe an explanation that will help. What our instrument does is we know the sun emits energy at all wavelengths, including X-rays, and those X-rays from the sun in this little diagram on the right are hitting the asteroid. And when the X-rays hit the surface of the asteroid, it excites the atoms in the minerals and that are on the surface of the asteroid. And those excited atoms, or excited electrons in the atoms, absorb energy and then release that energy, and they themselves emit X-rays. So we're looking at fluorescent X-rays from the surface of the asteroid. And that's what our instrument measures. And because our instrument measures the energies of the X-rays that it detects, we know enough about atomic structure that we know that X-rays of certain energy might be from oxygen atoms or magnesium or silicon, sulfur, iron, et cetera. So this is a way of fingerprinting at the atomic level what the asteroid is made out of. And at the same time, we have a little secondary instrument called a solar X-ray monitor, because how much we measure from the asteroid depends on what the sun is doing. If the sun is really excited, we need to know that, so that when we see a huge concentration of X-rays, we know it's the sun that's boosted the signal, not something special about a spot on the asteroid. Anyway, the highlight here is just that the students, it's the student work that went into this, starting with a class design in 2010 and 2011. That's the initial classroom design in 2011, and the final design was pretty similar. We put covers on the sides to keep out stray light, and we added a front radiator panel to keep the instrument thermally controlled. But other than that, the initial design out of a classroom setting was the design that we built and flew, and so that's pretty exciting. Building flight hardware is really almost a crazy idea, and space is really hard. It's very unforgiving. But even when you're trying to get to the launch pad, there's lots of struggles. We could always, as a NASA, because we were putting our spacecraft on board our instrument aboard a NASA spacecraft, we had to have a lot of NASA oversights, make sure that we were not going to do any harm. And every time we'd have a major NASA review, we'd get a big snowstorm. So we began to predict the weather based on the dates of our NASA reviews. You're trying to get, I think we have supply chain problems now. The key parts you've been waiting for, you learn were in a truck accident, and they're not coming for a while. You have vacuum chambers that fail and contaminate your parts, and you can't use them anymore. When you're building flight hardware, you put it in chambers and to vacuum chambers, and you put it on shake tables to try to make sure that it won't break when you launch. So you try to test it and see if it breaks. And then you find out, yes, it does break, and things get broken, and you lose cable connections. And anyway, you're always scrambling at the last minute to try to get it to fly. So we named our instrument the little spectrometer that could. And after all this that we went through, it turns out we could and did get on the spacecraft just before the Christmas holidays in December of 2015. So that was quite a present, a year-end present for our team. So that was December 2015. The launch was in September of the following year. And there's the Rex's spacecraft being launched on its way into space. And we had a small cadre of students who were able to get away and go down to Cape Canaveral and enjoy the launch and see the fruits of their labor head off and rocket off into space. So we arrived at our asteroid target, about 500-meter asteroid named Bennu, in December of 2018. And Bennu is pretty special asteroid because if this shows up, we think this is based on telescopic measurements we made way in advance trying to find a good destination. We think it's made of some very carbon-rich material, some of the oldest material in the solar system that we get some, but very few samples of as meteorites. And we wanted to get a fresh sample, uncontaminated sample of this asteroid because it may contain some of the earliest organic chemistry of our solar system. And that's not only important for the formation of the Earth, but it's important for the formation of life. And so we're really trying to look at the earliest ingredients of life in this sample that we're getting from this asteroid. And so the sampling occurred in 2020, and I'll show you that in just a moment. So our instrument, when you fly a flight instrument, you do calibration, and we looked at things in the astrophysical universe to calibrate our X-ray detectors. And the Crab Nebula turns out to be a very strong X-ray source for people who know about a little bit about astrophysics. And our goal was to measure these fluorescent X-rays off the surface of Bennu to try to map up what the composition is and the variation of that composition on the surface. But as I told you up front, we needed the sun to do all of the energizing of the surface. And we knew from the very beginning that the time when we were flying and would be operating at the asteroid, that we would be at solar minimum. But even at solar minimum, the sun undergoes periodic flares. And so this is a plot of time from 2017 to 2020. Remember, we arrived in 2018. And the little scatter data points in there are the measurements of the energies of the solar X-rays arriving at the asteroid. And as you go up the chart, you get higher and higher energy X-rays. And so we needed X-rays from the sun to be up in sort of this box region while we were there and making our measurements. And so we needed just the deeper colors there in the chart are the deeper intensities of the solar X-rays. And I'm not sure if you see anything, but the whole time we're there waiting to see X-rays glowing from the surface of the asteroid, the sun decided it was going to be incredibly quiet. And if you see X-rays from the sun in abundance hitting the asteroid there, we don't see them because we saw nothing from the sun and basically a very quiet, empty asteroid. So the asteroid did not produce the science we were looking for, but like so many things, and a great lesson for our students, we discovered something else. You discover things that you weren't expecting when you explore. And in this case, you see the asteroid Bennu off in the corner of this image. And we saw a small corner of space around the edge of the asteroid. And there in the edge, tiny part of the universe we could see, we saw this thing explode. And it was a transient X-ray binary black hole that decided to explode right in the small field of view that we had with our instrument. So we ended up discovering something. These kind of X-ray binary events happen about once per year somewhere in the universe, and our little instrument happened to be pointing in the right place at the right time. So sometimes it's very good to be serendipitous as well. So that's part of the science lesson. So we didn't quite achieve all the science objectives from the asteroid that we were hoping for, but our main objective was training students. And the little bars in this diagram are different students that were there for different amounts of time. It's a chart from 2011 to 2020, and the cumulative number in the end reached about 100 students. But each of these students is pointing to a little timeline chart bar on this graph. So what I'm most proud of and the real success of our experiment was the training of our students and the careers that they've launched. And they've gone off to work in all the major aerospace companies, JPL, NASA centers, et cetera. So it's really, really quite rewarding in that sense. All right, so the main mission of OsirisRex was to get a sample of an asteroid. It has this thing that looks like a mosquito proboscis that would touch down on the surface. This was an artist's concept of the smooth, gravelly surface of an asteroid that our thing that looks like an air filter would go down. We'd pump nitrogen through the filter, stir up the surface, catch the sample in the filter, and back away. And when we got to the asteroid, well, anyway, that's how the sampling mechanism looks. Looks like a car air filter touching down on the surface. And again, nice, smooth, pebbly, gravelly surface. And the asteroid ended up looking like this. The asteroid Bennu was full of surprises. It wasn't what we expected. And so it made it a very challenging problem to find a spot somewhere on the asteroid. And we found a region about the size of a small parking lot, which was big enough. There's a little circle in there that's about the wingspan of the spacecraft. So we found a place where we could descend to the surface and not have our solar panels get snagged by boulders, and we could go down and sample the asteroid. So this is an actual imaging of the sampling of the asteroid in October of 2020, and the gas canister fires and fills up the filter. And our requirement was 60 grams or 0.06 kilograms. And we think, based on imaging examination of what's caught in the filter before we put it into a return capsule, is we think we've got about 2 kilograms of material, and that we'll see in September of 2023. So we're thinking our overall mission is going to be quite successful, and it's going to be this primitive material from the very earliest part of our solar system. All right, so that's 2 missions. The third one to talk about is the farthest one. That's the New Horizons mission to Pluto. And I think in this series, you'll hear a lot about this. So I'm going to say just a few things, a little bit behind the scenes of the New Horizons mission. Other talks may be more about the science. This is a mission we launched in 2006. We reached Pluto in 2015 and 2015. And then my story with Pluto and the New Horizons mission goes back to the early 1970s, actually. But just a reminder, in case you needed any reminder about this entire series, is, of course, Pluto was discovered in 1930 by Clyde Tombaugh. And in the 1980s, I was a graduate student studying Pluto. And when you're the only or one of the very few graduate students on our planet studying Pluto, you get to meet the discoverer. So this is a favorite picture of mine of me and Clyde back in 1985. And I always have to remind people that I'm the guy on the right in that picture. And you may know, or you may have heard that Clyde, that his ashes are on board the New Horizons spacecraft. And so Clyde on the New Horizons spacecraft did get to, in a way, go to the world he discovered. So that's really very, very satisfying. All right, so the work I did on Pluto was back in the 1980s and then into the 1990s, and that was to try to make the first direct maps of Pluto. And there's a little cartoon here on the right that shows that there was a moon of Pluto named Charon, discovered in 1978. And we realized that basically once per century, actually once per 124 years, the orbit of Pluto's moon would become edge on when we see it from Earth. And we would be able at least in principle, to know that the moon of Pluto was transiting across the disk of the planet Pluto. So the moon was transiting across the disk of the planet. And it's like how we do exoplanet transits today. It's all the rage in the 2000s, but we were doing this back in the 1980s. We were just ahead of our time. And so if you can just carefully measure, even though Pluto is a fuzzy blob in a telescope and you can't see the moon and the satellite directly, you can measure the change in the brightness. And we would measure the change in the brightness as the moon of Pluto would transit across the disk in different parts of the disk. And we could use how the brightness changed, whether it was covering up a bright spot or a dark spot, to get the first direct maps of Pluto. And so we got on the cover of the Astronomical Journal. And for those who can remember the reference here, I bought 5 copies for my mother. Oops. Anyway, so what we found, and when we mapped Pluto, is it wasn't just all uniform. It looked like it had different dark bands at its equator and bright spots here and there, and bright poles. And the fact that Pluto had all this variation on it meant that Pluto has to be somehow kind of an active world. There has to be something going on Pluto, and that includes that Pluto has an atmosphere. And the atmosphere of Pluto was discovered by an MIT researcher named Professor Jim Elliott back in 1988, and our own Dr. Amanda Bosch was part of that discovery team. And so it's very exciting, and it's the fact that we're seeing these variations implying that something had to be dynamic about Pluto, and it led to this sort of integrated understanding or integrated further curiosity about Pluto. And I just throw this in because Cafe Press took our cover image of Pluto and put it on bumper stickers. And I've never seen a royalty check yet, but they said it's in the mail. All right, so we had started to map Pluto. We knew that Pluto has an atmosphere. We were starting to have specialized meetings on Pluto, and the scientists, the handful of scientists, basically a dozen scientists in the world who studied Pluto, were saying, we're stuck. We're learning amazing things, that Pluto is a very strange place, something different than anything we've ever seen before. We should go there. And we were basically graduate students, and we said, we need a mission to Pluto. Why not now? Why not us? And so we began to argue and advocate for a Pluto mission. And this is kind of how almost every planetary mission works. And it even is the way things as great as Hubble Space Telescope or James Webb Space Telescope come about. And that it all starts with basic research. And so basic research, in just as an example, you'll find basic research will do discovery surveys. And after you discover things, you start making follow-up measurements of what they are. And after you start learning about what they are, some of the things that you discover just don't make any sense, or they just totally baffle everything that you know and understand. So you find these tantalizing prospects that you'd like to learn more about. And you say, wow, if we could learn more about these objects, we have some really important science questions. And if we could answer those questions, we could really advance our understanding of the physics of how our universe works. But often then you're stuck. You can't make any progress because you've reached the limit of what you can do with your telescopes on the ground or even in orbit around the Earth. And that's the point where you make the case that you need a spacecraft mission. And so I call this the pyramid of planetary exploration. It's the way you build the case for basically the cost of a planetary mission. Spacecraft missions are expensive. So the story of Pluto is one that goes back into the 1970s and 1980s, where we had no fewer than 5 different pathways where we had proposals that were approved and then canceled. And we had to go back to the drawing board and start over 5 different times. And this really was mostly like the example of Lucy and the football. We were really feeling like Charlie Brown here, that we were trying to advance our mission. And every time we got close, Lucy would pull the football away. And there's a book about this called Chasing New Horizons, written by Alan Stern, the mission PI. And it's if you're not for the faint of heart, if you want to hear the story of how we got a spacecraft to Pluto, I highly recommend the book. All right, so there's a photo in the upper right of Alan Stern, our principal investigator. Alan is really the champion of the Pluto mission. His just persistence and undaunted determination that we needed to send a spacecraft there. So we were finally successful in 2001. This is the science team. There's members of Lowell Observatory there in the photo. Among them, Will Grundy is at the center. And so Lowell has had a big role in the New Horizons mission, not just Pluto itself, but in the entire mission. So we finally had the case for a mission to Pluto, and we got to the launch pad in 2006. So as I said, my career in observing and understanding Pluto began in the 1970s. And just to humanize what it is to do one of these missions, in that time span, you can go from being a kid with a telescope, you meet a girl, and you get married, a couple of kids come along, and basically your life happens in the process of trying to get a mission to the launch pad. So these are lifetime endeavors. They're not for the faint of heart, and you really have to be undaunted in your determination towards seeing these through. So finally, so my path began in the 1970s, finally in 2006, getting the New Horizons mission off the launch pad. And then after that, because it's Pluto, it's a journey of 3,463 days. And I know that number because I counted everyone, or 9.5 years to get all the way from the Earth to Pluto. And so in that next 9.5 years, one of your kids grows up to be a professional violinist who plays in Texas and recently in the Philadelphia Orchestra, a son who becomes an aerospace engineer. And life happens as these missions happen. So finally, in 2015, we get to the Pluto system, and it turns out that just based on how much mass in a spacecraft you can launch, when we got to Pluto, we knew the mission had to be a flyby. We could not carry enough fuel to slow down and stop. And so, and by the time we got to Pluto, we knew that there were multiple moons in the system, not just Charon. And so there was a lot of science we wanted to accomplish in the timing of our flyby in July of 2015. And so it took an enormous amount of people, time, and effort to basically write a ballet script or choreograph a script of how the spacecraft was going to point, which instrument on board the spacecraft was going to make its measurements. And this is just a portion of that ballet script where literally the spacecraft is turning, stopping, taking images, turning, stopping, taking images, all along the way of the encounter. So this all had to be planned and practiced before the approach because, picture that this is a mission that's taken decades to get to the launch pad, 9.5 years of flight to get to the destination. And then when it arrives, everything has to be pre-programmed on board. And because it's a flyby, you get one chance, and you get one chance only at doing it right. And so after all this work and effort, and this is an enormous, large team of people, there's only one thing you could do at the end. It was just buckle up for the last 1,000,000 miles. Hoping that there was not something fundamental that you messed up because you did not have a second chance. But as you know, from the success of the New Horizons mission, we did it. We were really quite successful. I'm just going to say one thing about the science. You're going to have lots of talks about the science of Pluto. This is largely the work of a graduate student at MIT named Alyssa Earle, also working with Will Grundy at Lowell. And we were mapping the composition of Pluto. So we're only seeing part of Pluto because some of it was in Arctic winter. The southern hemisphere was in long winter shadow, so we couldn't see it. But the northern part of Pluto, we could see, has a lot of different composition as you go from the equator to the pole at the top in this Mercator projection. And some of the work that's interested me is trying to understand what it is that's driving these composition changes with latitude on Pluto. So this is part of the mysteries we didn't understand and were revealed when we got there. And there's something I like to talk about is just to tell you that part of what makes Pluto so strange in how it operates is its orbital tilt. And you know, the Earth has an orbital tilt of 23 degrees called an obliquity. That's the tilt relative to our orbit. That's what gives us seasons. And we're nearing the time when the equator is pointed directly at the sun, and we'll have an equinox. And otherwise, one pole is favoring towards the sun or away and gives us our seasons. But in Pluto, the obliquity or the tilt is 120 degrees. And so there are times in Pluto's 248-year orbit where one of the poles and then alternately the other pole is more or less pointed directly at the sun. So it's a very different kind of seasonal variation than the Earth has. And what that means is the seasons, if you can use that term on Pluto, are very strange. In fact, there's an entire region that goes from 60 north to 60 south on Pluto that you could define as being tropical. On Earth, we say the tropics are where the sun can be overhead at some point during the year. And it turns out most of Pluto's surface is tropical by that definition. And it almost sounds like an oxymoron to talk about Pluto's surface being tropical. But from a sun point of view and sunlight point of view, most of Pluto's surface is tropical. And then the Arctic regions, the regions that can go into long winters, long continuous summers, or long continuous winters, go down very close to the equator. And so there's a much bigger Arctic region on Pluto than the Earth. And there are even regions in that mixed zone between about 30 and 60 degrees latitude that are sometimes in a tropical season and sometimes in an Arctic season. And so just when you start looking at all the complexity that Pluto experiences, plus the fact that its orbit is eccentric or elongated, and there are times when Pluto is further from the sun and closer to the sun, and even that orbit precesses over millions of years. Very, very complicated set of seasons and conditions on Pluto. And so I think that's what's driving a lot of what we see. And we're just still in the process of trying to unravel that. The last thing I'll say about Pluto, this is one of my favorite images of Pluto. This is the spacecraft is now on the far side of Pluto, and we're looking at a total eclipse of the sun by Pluto. And so we're seeing sunlight being refracted around the edges of Pluto, and we see blue light. And the reason that looks like a blue sky like we see on Earth is that most of Pluto's atmosphere is nitrogen, just like most of Earth's atmosphere is nitrogen, and the same scattering effect, something called Rayleigh scattering, that gives this blue scattered light color to Pluto. And I think we kind of knew that, but I think this image was so surprising and stunning in its own way when we were looking at the dark side of Pluto. Anyway, New Horizons continued on, and as you know, we're leaving the solar system, but on the way out, we're passing through the Kuiper Belt, and we did find an object along our path that we could go to, an object named erikoff that we saw in early January of 2019. And the thing I want to say about erikoff is it has this almost snowman-like shape, and we think it's two early planetesimals in the process of planet formation that came together at very low velocity and stuck together. And things are just so sparse in the Kuiper Belt that it never grows to a big planet. But what I love about what we saw about erikoff is there was an artist named William Hartman, who made paintings of what the early solar system looked like. And he said, here's what early solar system planetesimals look like, these things that are little things that are just barely stuck together. And it took us decades and decades later to finally see one. And it's just a credit to the artist eye being and the mind's eye of William Hartman being so insightful and the artist being correct. Anyway, you do something really cool like send a mission to Pluto, you get to be a stamp. And so these are really awesome. And I don't know if they're still available at the post office, but it's really fun when what you do turns into a postage stamp. The other thing about spacecraft exploration is somehow you become the rock stars in the universe, and the rock stars come to you. Brian May, you may know that Brian actually holds a PhD in astrophysics. When he was a graduate student, he was trying to decide, should I be a scientist or maybe this rock band thing will work out? And the rock band thing worked out pretty well. And then when the rock career kind of went quiet, he actually went back and finished his PhD. And but anyway, he came and was a scientific contributor to the mission, and just a great guy to hang out with. All right, so I still have one more mission to talk about. This is a mission called Lucy, which is named after the Australopithecus fossil, because we're going to the Lagrange points of Jupiter. And Lagrange points of the Earth are something we've talked about. These are the stable balancing points between the gravity of the Earth and the Sun. And that's where James Webb is being sent to one of these Lagrange points. And Jupiter has the same effect. If you think of the Jupiter and Sun, there are these Lagrange points called L4 and L5 in front of and behind Jupiter. And we think these are places where asteroids that formed very early in the solar system have been caught and been residents there since the very beginning of time in terms of our solar system. So we think they're fossil remnants of our solar system's formation, and hence the link and the name to the Australopithecus fossil. So it's kind of pretty cool when you think about it. Anyway, we got off the launch pad. Our launch date was October 2021. Again, patience is in order. We don't arrive at the first set of Trojan asteroid targets until 2027, and the second set in 2032. So again, my overall advice in space exploration is to be undaunted, but start young as well, because this is a career kind of endeavor. So I became involved in studying Trojan asteroids early in my MIT career. In fact, the first paper I wrote on Trojan asteroids with a student in a Europe program. The student was named Linda Salker. And it was an undergraduate research program, and we started writing papers about the nature of Trojan asteroids. Anyway, here's our launch in 2016. And I mean, 2021, just last October. And, so I've been involved in multiple missions and multiple launches. And, in the time it took to get this rocket to the launch pad, as Amanda said, I've retired from teaching at MIT, and I've turned to teaching rocket building to my grandchildren. And so the time marches on, and that's part of the message here. So it was actually very hard to think about ending a teaching career, but, we have fantastic success stories. Amanda Bosch is one of ours, of course. And with the Lucy mission, it's an MIT student named Kathy Olkin, who's the deputy principal investigator for the NASA Lucy mission. So even though one retires from teaching, you see that torch is being carried by your students. And that's really the most satisfying part of a teaching career, is seeing the success of your students. And so I always thank my students for everything they do, because that's the reward to a teacher. Our Lucy mission is very complicated in its orbital path, getting gravity assist from the Earth, getting out to the L4 Trojans. These are the names of the different asteroids we're going to encounter. There's the actual encounter dates at the bottom of the diagram, and then the set in 2027, and the last set in 2032, 2033. So a very complicated flight path. Along the way in the asteroid belt, we're going to encounter a small asteroid named Donald Johanson. The asteroid was named after the discoverer of the Lucy fossil. And even the asteroid itself was discovered by a former Lowell Observatory scientist and MIT student named Bobby Buss. And so a lot of MIT connections and Lowell Observatory connections, even to the Lucy mission. All right, this is a sort of an artist rendition of the different targets that we're going to see in the Trojan Clouds. And again, we're hoping that we're going to see some evidence of the very early formation of our solar system. I haven't really talked much about the instruments on board, but this is really a nod back to New Horizons, because we're carrying a derivative or copy or evolved version of a long-range imaging camera that was on board New Horizons named Lori, a imaging spectrometer named Ralph that was aboard New Horizons, and then a thermal spectrometer that was aboard OsirisRex. And so just something that happens in space exploration flight missions is this thing called flight heritage, where if you have an instrument that's flown successfully, it gives you high confidence that you can use it again on another mission. So it gives you confidence in your instrumentation, and in principle saves you money downstream. Oh, to close, just a couple of things that I'm looking forward to scientifically. We have evidence that sometimes when asteroids come really close to the Earth, the tidal stresses of the Earth can distort them and shake them up. And when we see some asteroids, there's some older sort of sunburned regions that are dark and red, and bright regions that we think maybe were freshly exposed because the asteroid was shaken up kind of like a can of nuts. And so this is something that in our work at MIT, we've predicted might be happening to asteroids that come close to the Earth. And we're going to have a chance to test this. This is actually a real thing. There is an asteroid named Apophis that will miss the Earth. And I'll say it 3 times. Apophis will miss the Earth. It will miss the Earth. It will miss the Earth. But it's going to come really close in 2029. It's going to come closer than the geosynchronous satellites. It's going to come 1/10. This outer circle here is the orbit of the moon. It's going to come within 1/10 the moon's distance on April 13th, 2029, which happens to be a Friday. And so again, there's no hazard here, but what it is a science opportunity that we have an object that's 300 times more massive than Tunguska, 5,000 times more massive than the thing that hit Chelyabinsk back in 2013. And it's going to be in one of these asteroids that's going to come really close. And we'd like to study it not only for the knowledge of the object itself, but what it means for understanding what we would do about an asteroid if one were ever really a threat. And we know when Shoemaker-Levy 9 went by Jupiter and broke apart before it hit Jupiter, the tidal stresses of a planet can be important. And so we're really interested to see what are the tidal stresses on this asteroid. It's going to tell us about how these asteroids are put together, whether we are going to see any evidence of seismic shaking or landslides, and basically what science opportunity does this present. So this is something that I'm working on even now, going ahead and looking forward to 2029 for this event. And again, just tying to students is we already studied this in a student project. And in fact, anytime you have a question you don't know the answer to, you assign it as a student project. And this was a student design mission that we did quite a few years ago. And we may see some derivative of this actually happening in 2029. And then the last thing I look forward to with asteroids is they may be part of the human plan for how we get to Mars. And the reason I say that is a little bit of a complicated diagram, but the bottom axis is just what's the mission duration it takes to get to Mars. And it takes basically about 2 years round trip to go to Mars and come back to the Earth. And on the y-axis, go vertically, is how much propulsion do you need? And so Mars missions for humans require a long time and a lot of propulsion. And to get to the space station is easy. You can go to the space station and stay there a long time. And the point of the diagram is that there are a lot of asteroids that we're discovering, have discovered and continue to discover, that are in accessible orbits from the Earth, that we could have short duration round trip missions that don't require as much propulsion as Mars. And maybe these are going to be practice destinations when we leave the Earth-Moon system and not go all the way to Mars the first time, kind of like Apollo 9 did before what Apollo 8 did and Apollo 9 did before and Apollo 10 before we tried to land on the moon with Apollo 11. So it's a way of testing our capability. So anyway, so just a little thought planted here that near-Earth asteroids could be human test flights before we ever reach Mars. We'll see if that comes to be. So there's a diagram. William Hartman painted this many years ago as a concept. So it's not necessarily new, but I think it's reemerging as a concept. And maybe this is going to be one of you there eventually reaching Mars. So the takeaway message here is here's to you, here's to our students. And all I can say is the most important thing for space exploration is to be undaunted. And with that, I'll stop and say thank you, and I'd be happy to take questions.
Thank you, Rick. That's quite the message. You definitely need to be undaunted. Really appreciate that. That was great. I do want to just open up the floor to questions, and I see we have one already, but if anybody else has a question for our speaker, please go ahead and type it in. But first, I wanted to let people know, because you were talking about the Lucy mission, we will have here in Flagstaff, for people who are local, on Friday, February 18th, both Kathy Olkin and Donald Johansson will be here at the Orpheum for a panel discussion, a night of discovery. So if you happen to be, in the Flagstaff area and you would like to come along, go to iheartpluto.org and get your tickets. So let me go ahead and start through some of these questions here. James asks about Pluto. So you were talking about how the surface of Pluto shows, that it's not a dead world, right? There's some activity going on there. And so James asks, with the moons orbiting Pluto, could that be the reason Pluto may still have some internal heat because of tidal flexing?
Oh, that's great. So Jane, that's a great question. So we'll just talk about Charon, the large moon of Pluto. It turns out that Pluto and Charon now are in a fully synchronous orbit. In other words, the same face of Pluto always faces Charon. Is kind of a great concept for Valentine's Day. You can imagine them in a permanent dance, always facing one another. And so there's very little tidal stress left over. It's all been dissipated. But to get to that final stable orbit configuration, there had to be a lot of tidal stress, losing a lot of orbital angular momentum and rotational angular momentum in order to achieve that state. And so we actually do have some evidence just in terms of what we see on the surface and how we see features pushing up from below on Pluto, that there could be a layer of liquid, seems incredible, underneath the surface of Pluto. And in part, it would be from the energy that is residual from that whole tidal dissipation. So that's a very great and very insightful question, Jane. Thank you.
That was a good question, yeah. We have another question from Kathy about time travel. So if you travel to Mars and come back, do you gain time or do you lose time?
Oh, that's great. So assuming you're going at normal rocket velocities, let's see. I think help me. Time slows down for you, and so you come back a little bit younger. So if you have a twin on Earth, and you come back a little bit younger, but we're talking maybe fractions of a second, I believe, than your twin. So you want to watch the movie Gravity, which is all about relativistic time travel, and they do a good job of getting it right in the movie Gravity.
Mm-hmm, mm-hmm. I was wondering, when you were talking about the Apophis flyby, the close flyby, which will not hit the Earth, as you mentioned.
The tabloids will tell you otherwise, I'm sure, when the date gets near. So that's why. So it doesn't matter what the scientists say, that tabloids will go crazy with this one.
Because it is going to be such a close flyby that doesn't hit, is there any possibility that it might split apart, kind of like Shoemaker-Levy 9 did?
Yeah. So first of all, I'll say it will be visible to the naked eye over Western Europe on the evening of April 13th. It'll be a third magnitude object going very fast across the sky. And I estimate 1 billion people will be able to see it with the naked eye. So it's going to be a big deal. So we're now doing the modeling of what how much stress is the object going to feel. And it turns out there's something called the Roche limit, which is at about 2 planetary radii, or about 2 Earth radii, which is really close for things are most likely to break apart. And Apophis is outside the Roche limit. It's at roughly 5 or 6 Earth radii. And so we don't think it'll break apart. We think it's going to have its rotation changed. We know it's going to get torqued, so its spin rate will change, and we just don't know how much internal flexing that's going to create. And an Apophis might not care in the least, and it may just say never mind, or it could change a lot. So it's that's right. That's the mystery. We just don't know, and that's why we need to look. We'll learn a lot because we don't have a clue.
Yeah. And even sometimes when we think we do know, we find out all kinds of things that we didn't expect.
Well, that's right. And for the Shoemaker-Levy impact on Jupiter, the predictions were from seeing nothing to kind of what we did see, which were major impact scars in the atmosphere of Jupiter. And so, so even when you think you know what's going to happen, usually there's a whole range of possibilities. So
right.
Anyway, it's a great knowledge opportunity. I think I call it a knowledge opportunity for planetary defense.
Okay, I'm going to keep going. You've got lots of questions here.
Excellent.
So we have another question from James. On the Lucy mission, is the spacecraft the same spacecraft for both locations of the asteroids? So both
Both Lagrange ones. Yeah, it's the same spacecraft that just keeps going. After we go to L4, we then have to come by and do an Earth gravity assist to swing out to L5. And so, yeah, it's one spacecraft that does a lot of work. And that was a real attraction in terms of NASA's approval. Getting NASA excited. There are always a lot of mission concepts. In fact, there's sort of a competition program there at two different price levels, basically, one called Discovery and one called New Frontiers and New Horizons. And OsirisRex are New Frontiers class. Lucy and Psyche are Discovery class. And they have to compete against other ideas. And so I think it was the versatility of that one spacecraft that was a great selling point for selecting that mission. Right.
Absolutely. So here we have a theoretical question from Ambry. What impact would this kind of space travel have for the rest of us on Earth?
Oh, so, so it's all about how does it impact our understanding of how we got here? I think space exploration, apart from just the human drive to explore and our curiosity, but the curiosity is driven towards our origins. How did we get here? I think one of the other biggest questions we ever face is: are we alone in the universe, or are we not alone in the universe? It seems incredible. Either answer is incredible, and that's our Buckminster Fuller would give that answer, that pick an answer, and either one has just incredible ramifications for the mind. But we don't want to think we're special. And so what is it about the chemistry and the temperature and the conditions in our little corner of our Milky Way galaxy that allow us to have this conversation today? And so I think we're really we're searching for our origins, and that's the knowledge we gain from these samples and going to these undisturbed places in our solar system are why we do it. And I'll just back up and say the Earth itself has, we have so many active processes. The Earth itself has almost no record of its earliest formation. It's all been mixed up, and that's why we have to go out into space. Going out into space is like going back in time.
That's right. Yeah, absolutely. So moving on, we have a question from Jasmine. How small is Ceres? So I did a little quick online research here. It's about 1,000 kilometers in diameter, which is almost 600 miles. But it has been visited by a spacecraft, and I don't know if you have any information about the Dawn mission.
Yeah, the Dawn mission was a spacecraft that used thermoelectric propulsion. In other words, used big solar panels, generate electricity, and expel gas, xenon gas, as its propellant, which made it a very flexible, versatile spacecraft. And it first visited the asteroid Vesta, a favorite of mine, as it turns out, and then Ceres. And so Ceres is the largest surviving asteroid in the asteroid belt. And so it really is looking at it what we call a protoplanet. In fact, Ceres is a dwarf planet, like Pluto is a dwarf planet. And so it's really just seeing a whole different class of planet that we'd never seen before.
Absolutely. Okay. Continuing on, we've got more questions. So James asks, what is the largest Trojan asteroid we hope to visit with Lucy?
Oh, I think it's Patroclus. I have to look at my own diagram to get it there, but about 100 kilometers across. And there's only one or two that are larger. I think the largest is Hector, and it's actually, we think it's kind of a pair of objects. It's a bit larger, but basically 100 kilometers across is the largest size we're we'll be able to see in the Trojans. And again, it's the trajectory that we can launch to, and the trajectory for the Lucy mission is designed to not only be flexible between the two Trojan Lagrange points, but also could we see multiple objects on one flight path, and so it becomes a little bit random which ones you see. But we think we have a great, and we're on course for a great selection of targets.
Yeah, absolutely. I was wondering if you could maybe say a little bit about how the sample from Bennu is going to come back.
Yeah, so on board this spacecraft is a capsule. And if you look at a picture of the OsirisRex spacecraft, I won't try to go flashing back to it, but you'll see there's a capsule. So the air filter, the capsule opened up like a clamshell. The air filter has been placed in the clamshell, and the clamshell is closed. And so basically the spacecraft is now headed back towards the Earth. All we have to do is to release that capsule, because the spacecraft is on a trajectory to hit Earth, basically. And so the spacecraft will release the capsule, and then the spacecraft has to thrust itself away so it misses the Earth, but the capsule has no further propulsion, so it will enter over the Utah desert and parachute. The parachutes will open and the capsule will be recovered.
Excellent. Sounds very exciting. Yeah, okay. It looks to me like we're reaching the end of our time. So I wanted to just say thank you once again, Rick, for joining us here tonight and really just telling us all about your experiences and sharing that with so many people, which is, it's not something everybody gets to experience is a spacecraft mission, and you have been on 4 of them. So it's really a treat for all of us here. So once again, I wanted to just say thank you to our sponsor, Findlay Toyota of Flagstaff, and thank you to our speaker, Rick Binzel. We really appreciate it.
Well, Amanda, thank you and your team, and it's a pleasure to be here. Thank you, and good night, everyone.